All right, welcome to Physics Video 3.2, which is the same as Essentials Video 2.2. There's some overlap in content here. We're going to learn about Newton's first law. As was the case with the last video, this is going to be a little bit on the long side, so I apologize in advance. I'm going to shoot for 15 minutes, but apologize if I go over. All right, so here we go. Newton's first law. We've learned what a force is. Newton's first law tells us how, well, all of Newton's laws tell us how forces affect the motion of an object. So we're going to learn the first one. Newton's first law, also sometimes called the law of inertia, says an object at rest will stay at rest and an object in motion will stay in motion unless acted on by a net force. A lot of this is kind of intuitive. If you look at an object sitting at your desk right now, maybe your computer is sitting on your desk, it's presumably sitting at rest, and it's going to stay at rest unless you push it over or something, right? And similarly, if you roll a ball down the hall, after you let go of the ball, it's going to keep moving, okay? So the object at rest is going to stay at rest. The object in motion is going to stay in motion unless acted on by an outside force, okay? So that is the way that this law is always written in books. And I think on a conceptual level, it makes a ton of sense. What I tend to find, though, is that students have a tough time applying that to problems. So I tend to like to rewrite Newton's first law at the risk of being somewhat egotistical. And I write it this way. Shoot, I thought I changed this. But so this is Hecker's version of the law of inertia. So here's my version of the law of inertia. It basically says that these three statements are equivalent. So that if one of these statements is true, they're all true. And if one of them is false, they're all false. All right, so here's the three statements. 1, 2, and 3. If one of those is true, they're all true. So here's the three statements. The net force on an object is 0. The acceleration of the object is 0. The object's velocity is constant, but not necessarily 0. Okay, those three statements all mean exactly the same thing. And the last two you already know. You guys know this, that if the acceleration is 0, then the velocity is constant. You already know that. All right, so what's new to you is this piece. If those two things are true, it also turns out that it's true that the net force is 0. Now keep in mind, that doesn't mean that there's no forces. It just means that all of your forces cancel out. Okay, so you might have a situation like this, where you've got, whatever, force of Roy pushing this way with 5 newtons, and the force of Sally pushing this way with -5 newtons. In that case, your net force is 0. And so, based on just this information alone, what we know is, since the net force is 0, it has to be true that the acceleration is 0 and the velocity is constant. Now keep in mind, that doesn't necessarily mean it's not moving. It just means it's not speeding up, slowing down, or turning. Okay? And that's where the big misconception comes in. A lot of people look at this drawing here and they think, oh, the forces cancel out, it's not moving. And it turns out there are situations where it could be moving. And that's sort of the main focus of this video today. It's one small concept, but one that people always have a tough time with. So we're going to spend some time on it here. Okay? So, to quickly review, here's Newton's first law. It's all or nothing. Either all three of these statements are true or none of them are true. Okay? So jot that down, put giant stars around it. This is, from now on, how I am going to write Newton's first law. Okay? I'm just going to keep writing those three statements on the board over and over again. That all three of those statements are true or all three of them are false. All right? So, what this means is that, in general, we need a force to change the velocity of an object. We need a force to get an object moving or to speed it up, but not to keep it moving. We need a force to stop an object or slow it down, but not to keep it moving. And we need a force to make an object turn, but not to keep it going straight. In other words, if you want an object to accelerate, if you want the velocity to change, we need a force. All right? This next chunk here is huge, and I already sort of alluded to this at the beginning of the video. It says, so please don't make the mistake of thinking that if an object is moving, there must be a force on it. All right? It is possible for an object to move at a constant velocity if there are no forces on it. Okay? I think what's confusing about this is you need a force to get it moving, but once it's moving, you don't need a force to keep it moving. And I think that this first example here I'm going to show you will help clarify that a little bit. Okay? So if you haven't already done so, pause this and write it all down. All right, so here we go, the bowling ball example. All right, so what I want you to do is I want you to imagine a little kid. I'm thinking like 3, 4 years old at the bowling alley trying to push a heavy bowling ball down the lane at the bowling alley. All right, to keep things simple, we're going to pretend there's no friction. which, you know, I mean, bowling alleys tend to be pretty smooth. So although we're oversimplifying it, it's probably not that much of an oversimplification. All right. So when this happens, when you go bowling or this little kid goes bowling, there are four distinct parts to the ball's motion. And we can talk about them all in, you know, using Newton's first law. All right. So the first part would be the ball sitting at rest on the floor, right? The kid puts the ball at rest on the floor, and he's getting ready to push it, but he hasn't pushed it yet. So at this point, there's no forces on the ball. It's just sitting there. And as a result, the net force on the ball is 0. It's not going to accelerate, and the velocity is going to remain constant. In this case, it happens that the velocity is 0 because it's not moving and it's staying at rest, right? Okay. Just as a quick side note, technically there are some forces on the ball. There's some up and down forces. Gravity's pulling the ball down, floor's holding it up. Those don't affect the motion of the ball, so we're not going to worry about those for right now. We're going to focus on horizontal forces today. All right, so that's the first part. An object at rest stays at rest. The velocity is 0. There's no forces on it, so it doesn't accelerate. Okay? So the second part of the ball, the kid pushes the ball, right? He wants it to go down the lane, so he's going to push on the ball. All right, so since the kid is pushing the ball forward and nothing is pushing it backwards, there's going to be a net force, right? Check it out. Here's the force of the kid pushing it forwards. So whatever, maybe he pushes it with, I'm going to make up a number here, maybe he pushes it with 50 newtons. All right, so in this case, what's going to happen is our net force is 0, right? Oh, no, it isn't. Sorry. Our net force is 50 newtons, right? Because the kid is pushing it with 50 newtons. And as a result, the acceleration is not 0, right? Since the net force isn't 0, the acceleration can't be 0. We're going to learn later on how to calculate that acceleration. But for now, what you need to know is the acceleration isn't 0, so it is accelerating, which means the velocity is going to change, right? That's why the ball starts moving, because the kid put a force on it and changed the velocity from 0 to whatever. Okay, so let's see if this works. I have a little video here. I've never done this before. I'll fail. All right, here's the video. So there's our kid pushing the ball. It's at rest. The ball stays at rest until the kid pushes it, and then it starts moving. So right there, we're focusing on this portion of the video, right there, where his foot is in contact with the ball. See that? He's changing the velocity of the ball. Before he touches it, no net force. Now there's a force that changes the velocity. Okay? So again, we're focused on from there to there. Foot in contact with the ball. There's a force on the ball that changes the velocity of the ball. The velocity goes from 0, velocity 0, velocity 0. There's no force on it. Force changes the velocity. Okay? So that is part 2. All right? Part 3 is the ball rolling down the lane, right? After the kid stops pushing it, the ball keeps going, right? But since the kid is no longer pushing it, there are no forces on the ball, right? The kid can't be pushing it if he's not touching it. There's no forces on the ball. So now, once again, check it out. The ball is moving this way with some velocity, right? Maybe it's, whatever, 2 meters per second if you got it moving at, right? Probably not even that fast, but whatever. The ball is moving. Since there's no forces on it, that means the net force is going to be 0, the acceleration is going to be 0, and the velocity is going to stay constant at, that's an at sign, 2 meters per second. In other words, the ball's not going to speed up or slow down because there's no force to make it speed up or slow down. Okay? So here's the video for that. So different kid. Thank you, YouTube. Thank you, parents of somebody. All right, so she's going to put a force on the ball. Now the ball is moving, and now the ball keeps moving at a constant velocity. Look at the ball. It's not speeding up. It's not slowing down because there's no forces on it. She's not pushing it forwards to go faster. There's very little friction to make it slow down. So it just keeps going at a constant velocity until there's an outside force of the pins pushing the ball, and that causes the motion of the ball to change. Okay? So, oh no. All right, how do I escape out of here? There we go. All right, so that is the third part of the ball, the third part. And again, I want you to understand, a lot of times people look at this and they go, oh, there's no forces on it. It's not moving. That is a really common misconception. Here, there's no forces on it, so the velocity doesn't change. That's the point of this example. Okay, so the fourth part then is the ball hitting the pins, right? So eventually the ball gets down to the end of the lane and that's supposed to be a bowling pin. Worst bowling pin ever. Deal with it. All right. So what's happening is the ball is moving this way with a velocity of, what did we say, 2 meters a second? And the pin is going to push it this way with some amount of force. That's going to cause the ball to slow down. It's not enough force to completely stop it, so the ball will continue along until it hits the wall at the back of the lane, and that'll exert enough force to stop it. Okay. So there we go. Newton's first law. Notice that now our velocity is going to change, right? So there is a net force that's not zero. All right. So now we need to do an example with friction. So this is the last example. It's probably going to take me more than 5 minutes, but I'll try to keep it as quick as I can. All right, so the big freezer example. So I want you to imagine a large freezer sitting at rest at the center of a warehouse. All right, Roy is going to push the freezer across the floor. However, the floor of a warehouse is significantly rougher than the bowling alley, so we got to consider friction this time. So here's what you got to know about friction. Friction is lazy, and it's going to always exert as little force as possible to prevent the two objects from sliding across each other. Okay, that'll make more sense here in a minute after I do an example. So for now, just jot it down. All right, this next thing is important here, right here. When two objects rub together, there's a maximum amount of force that friction can exert. The amount varies depending on what the two surfaces are and how tightly they're being pressed together. But what you need to know is in any given example, there is a maximum amount of force that friction can exert. Okay, and that's what determines how hard it is to get the object moving. Okay, so this last bullet kind of summarizes. If friction is able to prevent the objects from sliding, it's going to do so by exerting as little force as possible. Okay. If the two objects are sliding, then friction is always going to exert as much force as it can so that it can stop that motion. Okay. So there we go. That I think will become a lot clearer here as we work through the example. Okay. So on to the example. So here's our big freezer full of yummy ice cream sitting at the center of the warehouse. Roy likes ice cream, and he's going to steal the ice cream. Unfortunately, the freezer's locked, so he's going to take the whole freezer. So suppose that in this example, the maximum amount of force that friction can exert is 400 newtons. All right. Again, I want you to understand that's specific just to this example. All right. If I give you another example later on, that number might change. Okay. So in this example, the most force friction can possibly exert between the freezer and the floor is 400 newtons. So in the first example, Roy is going to push the, sorry, it says box here. That should say freezer, with 100 newtons. All right. So let's draw it. Here's the box. Right now it's not moving because it's just sitting at the center of the warehouse, so the velocity is 0. Roy is going to push it. We can assume he's pushing it to the right. It doesn't explicitly say that, but he's going to push it with 100 newtons. Now, friction doesn't want the box to move, so it's going to try to prevent it from moving. So the question is, does friction have within its power enough force to prevent the motion, to keep the velocity 0? Friction is going to try to keep the velocity 0, which means that it's going to try to make the acceleration 0 and the net force 0 if it can. So to do that, friction would have to push this way with a force of negative 100 newtons. And because 100 newtons is less than 400 newtons, it's able to do that. Okay? So there's our drawing for this one. Friction's able to prevent the motion by exerting a force of 100 newtons. Now, sometimes people say, well, why wouldn't this be negative 400 newtons? If friction can exert 400 newtons, why wouldn't it exert that? Well, think about what that would make the object do. If you've got 100 newtons to the right and 400 newtons to the left, wouldn't that make the object move this way? And that doesn't make sense. When you push something but don't succeed in moving it, it doesn't just move back towards you. All right? So the idea here then is Roy is trying to move it, but he is unfortunately not exerting enough force to get it moving because freezers are heavy, and as a result, there's a fair amount of friction between the freezer and the floor, and so it just doesn't move. All right, so Roy is frustrated at this point. 100 newtons does not make the box move. So for the full 10 seconds, the velocity is going to stay 0. It doesn't move. So now he ups his force to 200 newtons. So we're going to get the same thing. We're going to have our force of Roy, 200 newtons. Friction is going to try to stop it. It only needs 200 newtons to do that. And as a result, the velocity, which began at 0, stays constant because our acceleration is 0 because the net force is 0. Okay? And the whole key to this is that this 200 newtons is still less than that 400. Okay? So, third example, more of the same thing. It's still not going to move because 300 newtons is not enough to get the box moving. Okay, but what I want you to be aware of here is that as Roy pushes with more force, friction has to work harder to prevent the motion, right? Okay, so we're still going to have a net force of 0, our acceleration is still going to be 0, and the velocity is going to stay constant at 0. Okay, so Roy, determined, pushes now with 400 newtons. What am I at? So here's our force of Roy, 400 newtons. Friction still doesn't want it to move, and we're getting close, right? But remember, friction can exert up to 400 newtons, so it does exerts 400 newtons to make it so that the net force is 0 and the acceleration is 0, which keeps the velocity constant at 0. So the obvious question is, what happens if he pushes with more than 400 newtons? Well, let's find out. So this time, he pushes with 401 newtons. So what's going to happen now is Roy is very determined to get the ice cream. He pushes with 401 newtons. Now remember, friction doesn't want the box to move, so it's going to push back on it. But the problem is, friction can't exert 401 newtons. It can only exert 400 newtons. Okay, so at this point, it's going to do everything it can in its power to prevent the motion. It's going to exert its maximum force of friction, but it's not enough to prevent the motion. So now we've got a net force of 401 newtons plus negative 400 newtons gives you a net force of 1 newton. So now the freezer is going to accelerate, not very quickly because our net force is very small, but it's going to accelerate. So the entire time that Roy pushes with this 401 newtons, so for the full 10 seconds, the velocity is going to get bigger and bigger and bigger and bigger. Okay? So eventually we'll learn how to calculate that acceleration so we can find the velocity, but for now let's just make up a velocity. So let's suppose that at the end of the 10 seconds, it gets to a final velocity of, I don't know, whatever, let's go 4 meters per second. And I made up that number. It's not really significant what number I picked. Okay? So in part F, let's see what happens. It says he reduces his force to 400 newtons. So check it out. This is huge, you guys. This is the whole point of this. All right, so here's our freezer. Right now, the box is sliding to the right with a velocity of 4 meters a second, right? Because that was where we ended on the previous one, right? Okay. Roy is going to push this way with 400 newtons. Friction doesn't want it to move. Now, because the box is moving, friction is going to do everything in its power to stop that motion. So now our force of friction is negative 400 newtons. And the mistake people always make is they say, well, it stops. That these forces cancel out, so it stops. And that's not the case. What's happening is because Roy's pushing it forwards, he's trying to make it go faster. Friction is trying to make it go slower. The two forces cancel out, and it doesn't go faster or slower. It doesn't accelerate because the net force is 0. So it's going to just keep going at 4 meters a second. This is exactly the same as if friction wasn't here and Roy wasn't here. It's the exact same thing as the bowling ball going down the alley after the kid pushes it. There's no force on it, so it doesn't speed up or slow down. Okay? Here, the two forces cancel each other out, so it doesn't speed up or slow down. All right? So what if he pushes with a little bit less force? I think this might be the last slide. If it's not, it's pretty close. So now what's happening is the box is still moving at a velocity of 4 meters a second. Ooh. Force of Roy is 399.9 newtons. Remember, because the box is moving, it doesn't want it to, and so friction is going to do everything in its power to stop it. So now the force of friction is still negative 400 newtons. Okay? The reason for that is because it's already moving. All right? In the previous examples back here, when he pushed with 300 newtons, it exerted just enough to cancel it because it wasn't moving. But now that it's moving, friction's going to exert its maximum force. So now our net force actually turns out to be negative 0.1 newtons, and so now the box will slow down for 10 seconds. Okay? If he completely stops pushing the box, what's going to happen is this. The box is moving this way. Friction doesn't want it to move, so friction pushes backwards with negative 400 newtons. And there is no force of Roy. Okay? The box is still moving forwards because he had pushed it, you know, at some velocity. I don't know what it is, something a little less than 2 meters a second. Maybe whatever, 1.5 meters a second. But it's going to keep moving that way now. And then friction is going to cause it to slow down. Okay? All right. And there's a fun link of a cat jumping into a box. Oh, I'm over 20 minutes. Sorry.